So welcome everyone to another session of Husky Highlights. Our first speaker is Dr. Peng. He did a project called Towards High Quality Inference Services in Mobile Edge Computing. So take it away, Dr. Peng.
So I can get started. So the title is Towards High Quality Inference Services in Vehicle Edge Computing. And this is the work I have started actually using the SRCP fund and over the last 2 years. And for today's presentation, here is the quick outline. So basically 4 sections. And to get started, we need to introduce some research background. So basically the motivation, as many folks here are working on, is about machine learning and in artificial intelligence, and particularly for my background in the Internet of Things field. So we see dramatically increasing of the use of machine intelligence to design new and emerging applications and systems, not only IoT, but even larger systems. And for these applications, focusing on the videos. So video is primary data, and they could be applied to traffic management, potential intelligent traffic management, and personal cognitive assistance. And as well as you can see on this picture, like pervasive everything reality. So that's the XR. So all of these applications, they require the intelligence in the background to support the success of these applications. And that's why computing, well, together with networking, are becoming more and more important for these applications. But in order to support these applications, traditional cloud computing is not sufficient, or we can consider it's kind of outdated. So I think less than 10 years, edge computing was brought up. And compared to cloud computing, the edge computing, the idea is push the computing location from cloud to the so-called network edge, where it is maybe just consider one hop next to the end users. And for this computing servers, they are not as powerful as cloud, but they are much powerful compared to the end users, or particularly the mobile devices. So for, as I mentioned, those applications, if they require intelligent services, the mobile devices, they may not have sufficient computing power as well as just general energy to serve the computing needs. So the edge intelligence idea is, let's do the intelligence computing job on the edge server. So we're talking about intelligence computing, not just traditional computing. For example, the web service. We're talking about the computing job that may take relatively longer time, but which means it's above the typical tolerance range, say 100 milliseconds for the end users. So we want to deploy these inference computing jobs. We can view them as trained machine learning models on the edge servers and offload the computing tasks, the inference tasks, particularly from mobile device to these edge servers. And then by doing this, we can reduce the end-to-end service latency. We can increase potentially the inference accuracy, because user can only tolerate certain level of end-to-end latency. If you spend too much time on networking, you cannot spend much time on computing. But reducing networking time can increase the computing time, which means some high accurate models can be used. And then finally, saving the computing power on user device, just to use the edge device. That's another motivation. So of course, talking about privacy security, so users don't need to offload their data to a remote cloud server for those concerns. Okay, and this is the general trend over the last couple of years, but just maybe since 1 year, or just right in the year when I started my SRCP project, the vehicle edge computing was brought on table. So the general idea is we talk about the server locations. It's from the cloud pushed to the edge, actually in between the edge and the vehicle. That's my focus. There is another tier but people stop talking about it. We consider that's the so-called parked vehicles or parked stations. You can view this as when you go to the football game, you may see some mobile cellular trucks just outside the field. That's a similar idea. We call it parked stations. And now, just one step further, we talk about the vehicles. The reason is we see many new vehicles coming equipped with powerful GPUs. For example, Tesla itself, it's not used for others, but used for itself to train the models on the way. And that's actually extensive use in the autonomous driving community. They were talking about how to train the models on vehicles in place. So that's one change. But on the other side, the changes for the vehicles, starting from day one, it's used for travel, but now it's used for delivery. Okay, and then eventually it can be also used for computing, because that's by default, we change from gas vehicles to electrical vehicles, and more powerful computing power devices are equipped installed. So that's so-called vehicular edge server. So the server itself is not static on some particular location. It's moving all the time with powerful GPUs, with sufficient power supplies, and with cellular or Wi-Fi connections. And more importantly, they're mobile. Okay, with all these changes, that comes to my motivation for this work. So for this work, we see growing need of pervasive intelligence-driven services, as all those applications I mentioned. Those applications that share some common attributes: latency critical, computing intensive, and also accuracy sensitive. Because if the result is not accurate enough, the serving body, human beings, cannot use them. And on the other hand, for existing infrastructure, particularly the static edge computing servers, so for example, several towers, all the Wi-Fi or the local routers, okay, they have the problem of peak time server overloading, because it's just limited server racks, different from cloud. Cloud is considered infinite. And for the signals, it's somehow short range. So whenever users are moving, they may move out of range. And more importantly, because they are static, they cannot tolerate potential natural disasters or just human accidents. Okay. And finally, I mentioned those electrical vehicles, and there could be more. I will show you some examples. Autonomous moving systems, not just vehicles. Vehicles so far is a bit far away from that, but maybe in a couple of years. But there could be other robotic devices. Okay, so like the drones or like delivery robots. Okay, so putting all this together, that motivates this work to replace, actually renovate the existing computing or edge computing infrastructure to be the vehicular edge server enabled infrastructure. So in this infrastructure, we could deploy different robots, maybe small, maybe big, just as the size of the vehicle, maybe flying, just like the drones. All these potential candidates to be used as the vehicular edge servers. So they could move either on road or fly to different locations to serve the needs of the local computing, consider the hot areas. So, but to do this, the benefit I listed here, only three major ones, talking about the efficiency of the overall server use, and talking about the flexibility, because it can save a long time on getting permits, installing new towers, choosing the location for the servers. It's just on road. And lastly, that's about another motivation, as I mentioned, and also highly recommended by NSF, is the resilience, because that's the next generation for our cyber infrastructure. It must be resilient. Okay, so putting all this together, we do see the benefits. But the problem is, this is not a small problem. Overall, that's a big problem. So talking about just in my field, we view this as an optimization problem. So because the overall objective is to maximize the quality of intelligence. So you may have heard about quality of service, but quality of intelligence is about the inference accuracy and inference latency. And at the same time, because we are using the user device, we're talking about servers, we need to consider the user equipment power consumption as well as the cost or the efficiency of the server. And again, related to this big picture, this big scope, the objective is clear, but the constraints, there are too many variables there. From the server perspective, from the user perspective, from the network perspective. If you can imagine this in the mathematical format, it's a long list of constraints. And also for the output of this problem, there could be many different configurations or setup for the whole system. There is no easy way to get the optimal solution, okay, in one step. So of course, we want to solve that problem. We see the benefits, but at least to me, I cannot see any feasible solution to get the final answer quickly and in one step. So in order to solve this problem, I divide this problem into 3 tiers. Actually, in my SSGP font, I think I focus on the infrastructure tier, and I also did get into other tiers with the help of SSGP font. That's the good part of it. Okay, so from infrastructure tier perspective, it's about just how to deliver the vehicular edge server resources to particular locations. And then once the resources are delivered, we need to think about, okay, in that particular area, there could be different group of users, how those users could use this already delivered resources. And lastly, at the user tier, even a user has been assigned or selected a vehicular server. So the real-time condition could change. For example, the network condition may be bad, or the server condition may be suddenly crowded or overloaded. So how to change the already allocated resources for the dynamic use, that's at the user tier. So my work with the help of the SRC fund is try to see at each tier how to solve each tier's particular problem, and then finally how to potentially generate some cross-tier problem and solve those to make it even better. So at the infrastructure tier, the main job, as I mentioned, is to allocate the resource to different hot areas. And to do this, we need to consider the actual dynamic changed computing needs. So that means the overloading condition in each area may be different. And also we need to consider there may be already existing computing resources there. So the use of dispatch of the vehicles may not be necessary for some area for some time. And then we also need to consider the area may be too big, a citywide area, so we need to divide it into smaller areas, just like how people use the cells for the cellular services. And then there could be one or more vehicles to be dispatched, and those vehicles could be collaborative, could be independent. So at this tier, I have 3 students that's actually they are actually working in this area. I will show you some preliminary work they have started or completed. And at the edge tier, as I mentioned, is once the resource has been delivered to a particular area, we need to figure out how the users can be scheduled or guided to use the resource. In this case, the user and the vehicle server could collaborate, or they don't collaborate. If they could collaborate, you can imagine that users, all the vehicles could move together towards some direction for some time. So in that case, users could be associated to that particular server for as long as possible. So the service don't need to be disrupted. But on the other hand, for example, the bus, they won't wait for the user. So the bus will keep moving. So in that case, the user's computing job may need to be offloaded from one server to another server continuously. So how to make sure this potential temporary disconnection or interrupted service could be minimized, as well as improving the short time inference quality. So that's also, I think I have one student finish part of the job here, okay? And at the user tier, this may be closer to what you can imagine because this is particular about how to use the actual results if the user has been assigned to a server, or in other words, the vehicular edge server. Okay, so in this case, how we could change the amount of GPU resources to the user dynamically, the GPU core or GPU memory, or how we can choose the radio. Sometimes it could use cellular, sometimes it could use Wi-Fi, or in extreme case, Bluetooth could be used because they have different benefits on communication speed and throughput for data. And lastly is, as I mentioned, accuracy is one consideration. So is that possible that if the server is not powerful enough, just because of heavy use, can we just change the model to be used? So certain level of accuracy can be obtained, but it may not be the highest, but still satisfiable. Okay? That's at the user tier. Okay, talk about these three tiers. I have some published work already. They were at different tiers, user tier, edge tier, and there are some ongoing work. So I list the four, actually there should be six. Okay, I only list the four major ones. And the students, they are working on this different tiers. And so basically they're trying to get their work published. So I prepared two work, the published work, and I think I'll only talk about one into a little bit more details. That's about the first one, the adaptive acceleration of inference service at the network edge, just for this user tier solution. Okay, and this work was published in IEEE Mobile Cloud just in last summer. Okay, for this solution, we assume that the server resource has been delivered or allocated to some area, and the solution tries to dynamically adjust the operations on the user device and edge server. So what's the adjustment? The adjustment includes the model being selected for the user, include what the frame size the user should use to capture the surrounding environment, and also include which edge server to be, or which particular GPU core to be used for serving the request. And objective include many parts, but definitely it includes the accuracy, the latency, and particularly also to maximize the number of user requests can be served, because we don't want to only serve one or small number of users. That's a waste of the delivered results. So talking about this topic, we investigate two major directions of existing work. One is about so-called inference request routing. This may hear about something about load balancing. That's similar idea. It's just to decide, given different requests, but it's not just general computing requests, but inference requests. They need to figure out how to use the particular GPU, which is different from CPU. So how to use the particular GPU resources. And there are a couple of existing work that tries to figure out how to route the request to different servers. And another approach is to dynamically adjust the quality of the inference job. So basically the idea is, as I mentioned, you could choose different models at different time, one fit for all, or always choose the best one to use. Or you could choose to, for example, change your frame resolution from 1080p to 480. So that's a dynamic input size change. So using this technique, the users may be satisfied with the latency and accuracy. This is so-called inference quality adaptation. And for our work, we put these two research directions together because we see the gap that for each direction, they cannot help each other. They actually cannot fill the whole gap. So our solution combines these two techniques together, but at the same time, we try to be compatible with the large range of inference serving software and hardware. So we don't need to change the low-level details. Okay, that's for this work. And Here's the boring part. You may not like it. It's just the mathematical format of this problem, but I already tried to reduce the notations to be used here. In general, the most important thing here is to decide which request, the inference request, to go to which server, and on that particular server, which particular model to execute. So this is a general optimization problem, which is a typical thing in my work. And to solve it, of course, you could say, let's try all the different combinations to solve it. That's definitely possible, but it may take much longer time in practice. So in our solution, we try to design some so-called online algorithm that can serve the incoming requests as soon as possible. So we propose this heuristic solution based on the traditional, or say classic bin packing problems approach. And in this approach, we view each item as the request session, we view the server as the bin, and we view the server's capacity, in our definition, additional frame per second to be added to the server as the capacity of the bin. So we try to see which server, or in other words, which bin that can be used out of potential many bins. Okay. And by doing this, we have developed the algorithms that include two phrases. The phrase one is to try to see, okay, let's just accept this request without adjusting all the existing requests on the server. So no change to existing customers. But if that won't work, what we try to do is, we'll try to demote the existing requests on the servers already. So let's say, let's just create some space for incoming ones. And if that works, then after that, we gradually bump up the accuracy for the accepted server requests. But if that won't work, say, okay, we cannot create any space for this incoming request, then we have to reject it. So that means all the existing requests are protected. Okay, so this is our online solution. But this online solution needs to be executed as fast as possible. But in practice, it may not give you the best result. So we also developed some so-called offline solution. The offline solution would run somehow not that frequently. You can assume that online solution runs upon every single request coming. But this offline solution, it will run periodically, a couple minutes. So the idea is we need to gradually replace or do some replacement of the existing requests from server to server. So the idea is we can efficiently use the existing server resources. So the intuition is the larger an atom, say, the available configuration for some requests, then it is harder to find a bin that has enough space, so the server's capacity. So how to do this? We just, as I mentioned, over time, couple minutes, we sort all existing requests in some ascending order by the available configuration to satisfy this request, because this request may require high accuracy, the other request may just need a very minimal accuracy, and this request may ask for short latency, but the other may tolerate long latency. So sorting all the configurations, and then we try to tackle or serve the request that's very hard or the most difficult to be served. And then gradually we replace all different requests to different servers using the server resources. So this is periodical running offline solution. And for this solution, we implement this solution through three major software components. And we deploy our software components to both user device and edge server to verify its performance and try to see through simulation and test by experiments. I didn't show you the simulation results, but just want to give you this idea, like I think I used the SSP fund to buy some devices here. So we use primarily the just nano devices, the equipped actually installed into many mobile devices already. We build this platform with low scale and mid scale and large scale Jensen devices. And also we test the solutions with the laptops, low end, high end, try to mix up and create realistic environments for the testing. And I save the results in terms of the performance because that takes time. It's not technical conference. So I just want to show this picture to appreciate the support of the SRSP fund. And what I want to mention, I copied the picture from the Office of Research webpage about this picture. I think that's a good one to use. And big thanks to the SRSP fund because, as I mentioned, this overall problem is a big one. If I just submit individual tier for external funding, it may be hard. So with the support, I can get started working on different tiers, figure out what's the particular problem in each tier, and develop a more comprehensive proposal. And also I can attract students to build the workforce pipeline because over 2 years, I have a couple of students graduate already and new students are picking up. And for the next step, as I mentioned, a more comprehensive proposal is under development. Actually, I think it's almost done. What I need is just next year during my sabbatical year, I'm going to go out and look for particularly the collaboration from Puget Sound, the Sound Transit and Uber. I mean, talk with some guys, some folks, engineers at Uber. So as I mentioned, this is about the vehicle. So buses and taxis, there are two representative vehicles to be used on road. So I want to deploy the server, the hardware and software into real vehicles on road and do the actually on-road test. That's the next step for maybe at least 2 years. That's in my plan. Okay. Yeah, so that's all for my today's talk.
In the introduction of your presentation, you mentioned about the vehicle-based, kind of, I don't know the exact term for that, but you are going to use or interested in using the computing power from vehicles.
Yes.
So, most of the electric vehicles nowadays on the road are equipped with those, devices able to be used for the future communication, or what is the current status?
The current status is, as far as I know, they have the network capability already. So that's, I think, required for newer vehicles. I'm not clear about US, but actually in Europe, that's a requirement, so-called the vehicle network. That's a requirement for newer generation vehicles. But for the computing part, they are not required by the standard, but all those newer vehicles, they do have GPU resources. It's just those resources are primarily used by the vehicles themselves. They won't be shared with the users. So for my work to continue, I will simply just put one additional device to any vehicle, just like the bus. Because I think for Seattle campus, for the civil engineering department, they do have ongoing project by putting cameras with GPUs onto the bus to avoid potential collision with the kind of the pedestrians. So that's ongoing project I learned already. But as answering your question, so for the GPU resources, they do exist in many vehicles already. It's just they're not exposed to users to use so far.
Thank you so much, Dr. Peng.